Hi everyone, so I decided that I'm going to make this exam 1 review video to basically just reinforce all the concepts that you should know for this upcoming exam. This video specifically is going to cover all of the chapter 15 material, which is the organometallics, and I will be posting a supplemental video on the chapter 16 material that you need to know for your exam. So feel free to play, pause this, rewind it, do whatever you got to do, show it to your dog to get these concepts down. So without further ado, let's just jump right in. So let's start with the first class of organometallics. There are 3 of them, and these are the Grignard reagents. So the Grignard reagents have the general schematic of RMGX. Alright, so before I talk about what this Grignard reagent is, I just want to show you how the synthesis works. So if I took an alkyl halide like this, and I were to react it with pure magnesium metal and diethyl ether, could be THF, doesn't matter what the solvent is, then I would get an end product of MgBr. Alright, so let's just talk a second about the dipole moments of these molecules. So if we look at our reagent, the alkyl halide, we know that that bromine has a lot more electronegativity than that carbon that's next to it. So that means that we're going to have a partial negative charge on the bromine and a partial positive charge on that carbon. So if we were to classify this carbon right here, would that be a nucleophile or an electrophile? Well, it's going to be an electrophile. Okay? If we looked at our Grignard reagent, that magnesium actually has a lesser electronegativity than that carbon that's adjacent to it, so that means that our dipole moment is actually going to be towards the carbon. Okay, so if this is a localized negative charge at this carbon, would we classify that as an electrophile or a nucleophile? You said nucleophile, you're right. So the whole concept of this chapter is that we can use these metals, and that interference, I guess you could say interference, between that carbon and that halogen is actually going to switch the dipole moment around. So now we have this whole new class of carbon-based nucleophiles that we can manipulate and use in reactions. Alright, so some people are kind of confused on why the bromine still sticks around. So let me just talk about this for a second. That magnesium is actually naturally a +2 charged compound. So in order to have a net neutral molecule, we need to have some sort of halogen that's negatively charged and then some sort of carbon that's negatively charged. So that complex of this carbon, magnesium, bromine area, that is all net neutral. That's why the bromine still hangs around. Alright, so let's just move on to the next class of organometallics. That's the organolithium reagents. So the organolithium reagents have the general schematic of RLI. Okay, notice how there's no halogen there. So the synthesis is very similar. So if we took an alkyl halide and we did 2 equivalents of pure lithium metal and we dissolved it, let's just do THF for this time, we would get something like this. Okay, and you don't have to draw the waste product of the salt lithium bromide, but I'm just going to show it here. So let's just again talk about that dipole moment of our organolithium reagent. So that lithium is a lot less electronegative than that carbon, so we still have this dipole moment of this partial localized negative charge on that carbon and a partial positive localized charge on that lithium. So again, this is still a nucleophile. So let me just show you the proof of why we only have 1 metal here and not that halogen associated. Well, lithium is naturally in the +1 cation state, so all we need is a negatively charged R group like this to neutralize that whole molecule. Alright, so let's move on to the final class, the Gilmans. These are the most useful in synthesis. I'm sure you guys have already figured that out by now. So the Gilman reagents are actually synthesized from the organolithium reagents. So let me just start with a organolithium reagent that we just synthesized. And the way to get from the organolithium to the Gilman reagent is to just react with copper iodide and an inert solvent like diethyl ether, or a polar A product, excuse me. So what happens is that we actually have 2 equivalents of this reacting, and we're going to form a cuprate that looks like this. Okay, so that says there are 2 of these carbon chains attached to this coordinate complex, which is the copper lithium, and we don't really need to know the whole structure of it. Just know that this is the synthesis of that reaction. Okay, and I think that's pretty much a good summary of the organometallic compounds. Let's move on to specific reactions of them, all right? So all of these organometallic compounds can react with epoxides as nucleophiles and open these epoxides. So let's just go through an example of each one to kind of reinforce that. So if we look at number 1, this is a Grignard epoxide opening reaction. So remember that we are nucleophilically negative at that carbon, and we have to decide, we have a regioselective choice of which carbon we want to attack on this epoxide. We can choose the more substituted or the less substituted. Well, let's think back to organic 1 when we were doing SN2 reactions. SN2 reactions were governed by nucleophilic properties, and those nucleophiles could only attack the less sterically hindered side. Remember, we wanted to attack the side that was less hindered because that just made sense logically. We're not going to attack a very crowded carbon, we want to attack the less crowded carbon. So if you picked this arrow or this carbon, then you were correct. So let me just show you the mechanism, the shorthand mechanism for this. Let's just pick purple, why not? And we're going to take these electrons from that bond, attack at that carbon, and push that bonded pair of electrons up, all right? So let me just show you the product of step 1. The product of step 1 would look something like this. All right, and we would have a CH2. Okay, so that's the product of step 1. And the second step just is a protonation step for that alkoxide anion. So the final product should look something like this. Okay, so let's just talk about the stereochemical consequences that we had with attack at this carbon over here. Remember back into organic 1 when we talked about SN2 reactions, SN2 had inversion of configuration of that stereocenter. So think about this. If I were to attack at that carbon, this dashed methyl group should actually become a wedge, right? Okay, so that is true, that it should be a wedge. But I'm actually rotating it upwards, like 180 degrees. So if you took a wedge and you rotated 180 degrees like a pancake flip, it actually turns into a dash like that. So it looks like we didn't play with any stereochem here, but we did indirectly, all right? So that's Grignard epoxide opening. So let's move on to organolithium epoxide opening. All these organometallics follow the same schematic, so it's pretty self-explanatory. So ETLI. ETLI is just an abbreviation for an ethyl lithium reagent, so it looks something like that. And that is going to attack, remember we said it was nucleophilically negative at that carbon, so it's going to attack the more, or the less sterically hindered side, which is right here. So the mechanistic arrows for that, let's just go back to purple, would be something like this, okay? So the product of step 1, let me just draw that real quick, would be something like this. Okay, and then the final step is again just another protonation step, so it's going to look something like this. So now I just want to talk about why I only have one product in this reaction. So let's think about the possible locations that this organolithium reagent can attack from. So the epoxide is on a dash configuration, so that means the back side of this ring is actually completely sterically hindered. I can't attack from the backside of this ring whatsoever because of how bulky that epoxide group is. So that now only limits me to the front face of this molecule. Again, we just talked about how these nucleophiles can only attack at the less sterically hindered side. So this top carbon up here is sterically hindered by an additional methyl group. So that's why we actually only had one carbon to attack, and that was that carbon. So we only have one product there. If we didn't have this methyl group that was on that wedge configuration right here, then we would have two different products possible, but we don't. Okay? So let's just talk about the Gilman epoxide opening reaction. Again, the same thing we have been seeing this entire time. We're going to attack at the less substituted position. Remember, it is nucleophilically negative at that carbon. So the general schematic of this reaction is going to be these electrons attacking here, pushing that up. So the product of step 1 is going to look something like this. And then, again, step 2 is just that acidic workup step, so you'd expect something like this. And again, you can rotate around that sigma bonds and make it look a little bit nicer, but this is just a valid structure as well. All right, so let's move on to the next side reaction that we have with organometallics, and it's the unwanted side reaction of organometallics. So this is kind of something that Dr. Peterson mentioned, like in between, like moving on, and I think we should place a little bit more emphasis on what happens when we have this these organometallics reacting with a polar protic solvent. So there was a reason earlier that I said that the organometallics should be dissolved in diethyl ether or THF, and I took a picture from your textbook, and this kind of just shows the solvation of that reagent in solution. So these molecules, this diethyl ether, actually doesn't have any protons to give up to that Grignard reagent, so it's actually a very good solvent. If we had a polar protic solvent like water, then that proton would react with the Grignard reagent, and that is an unwanted side reaction that we don't like. So let's just look at this example over here. We have this, again, Grignard reagent, and we have a polar protic solvent. So remember, we said that they are nucleophiles, okay? So if we recall from Organic 1, we said that nucleophilicity parallels basicity, right? So we can classify the Grignard actually as a base, right? And we said water, remember if you remember from Gen Chem, it's an amphoteric substance, so we can classify that as an acid. So the acid-base reaction is going to predominate. So if I draw the structure of water and its Lewis structure, what happens is that these electrons are actually just going to grab a proton, and we're actually going to synthesize just a plain alkane. And clearly that is something that we did not want to happen, the synthesis of this alkane. So we have to be very careful with the solvents that we choose, because we want to prevent unwanted side reactions. So just be wary of that. We technically see like an epoxide with a Grignard as a step 1, and step 2 is a separate protonation step, because we can't mix polar protic solvents with these organometallics. I hope that makes sense. All right, so let's just talk about what the carbene reactions is. This is the end of chapter 15. So what is a carbene? And carbenes are these kind of funky structures. They're carbons that are bounded to only 6 valence electrons. So we have 2 electrons from one hydrogen, 2 electrons from another hydrogen, and then that 2 electron lone pair, and it's actually neutral. So I'll just write here neutral. So that's interesting. We have 6 valence, and yet it's neutral. So these reactions are very unique in the form that they form cyclopropane structures. All right, so that's pretty much all I wanted to say about carbenes. So let's just jump right into the 2 types of reactions that we saw. So the first one was dichlorocarbene synthesis. So when we see these 2 reagents, which is chloroform and tert butoxide dissolved in with an associated potassium ion, we really don't know what's reacting with this molecule. So whenever we have a group of reagents like this, let's just kind of figure out mechanistically what we're dealing with here. So let me just draw out the Lewis structure of chloroform. So it looks something like this. And let me just draw tert butanol. So tert butanol has this structure. I don't need to draw the spectator ion. There is an associated potassium hanging out. So terbutanol, recall, is a very good base. And what's going to happen mechanistically is we are going to deprotonate that hydrogen from chloroform. All right? So that's going to give me this structure. And these chlorines are so electronegative that one of those chlorines can actually just spontaneously leave at any given point. Remember, that's kind of something we saw with the rate-determining step of SN1 reactions. So then we just generated a dichlorocarbene. So this is actually our reagent that we're using in this reaction, okay? So it looks kind of confusing from first glance, but just take a step back, think a little bit. We have chloroform, terbutanol. What's the purpose of terbutanol? Obviously, that's a base, so it's going to remove that hydrogen from chloroform, and then mechanistically, we see that that chlorine can kind of just leave on its own, all right? So we want to show that this molecule is reacting with dichlorocarbene. So let me just erase a little bit to make a little bit more room. Okay, so I'm just going to redraw that dichlorocarbene over here. So we have two choices. This carbene can either react from the front face of this alkene or the back face. So let me just draw mechanistically those arrows. So these pi bond electrons are going to attack this electron deficient carbon. And then those lone pair electrons that are on the carbene are going to form another bond over there. So it's a single-step concerted mechanism. So let me just fix that. So there. Okay? So again, we can either attack from the front face or the back face. So we'd expect a mixture of products. So if you predicted this as your structure, sorry for the bad handwriting. I hope that's kind of clear. I know it's really crowded. But we can see that we have a cyclopropane on a wedge configuration over here. And we have cyclopropane on a dash configuration over here. All right? So remember that we have this single-step concerted mechanism, and we can either attack from the front face or the back face, and we're forming a cyclopropane structure. And do not forget the chlorines. That is a very common mistake, is just to draw the cyclopropane structure without the chlorines. All right, so I hope that makes sense. So the last one is the Simmons-Smith reaction, and this is the more practical, more realistic reaction that we see in organic chemistry, because we don't really like those two chlorines attached to a cyclopropane. It's not really stable. So what we like to do is just a plain cyclopropane addition to molecules. All right. So this one is called the Simmons-Smith reaction, and we don't really cover the mechanism at all, so I'm not going to talk about the mechanism, but just know that these three reagents are going to form a cyclopropane structure, again, either on the front face or the back face of the epoxide. So if we kind of can visualize this structure, okay, and we can either attack from the front or the back face, so this would be attacking from the front face. So attacking from the back face would be something like this. But again, since this molecule has an internal plane of symmetry, this would be a meso molecule, so we only need to draw one of them. Okay? So those are the two carbene reactions that you should know. Pretty self-explanatory. So finally, let's conclude this video with a synthesis practice that I think is pretty important or pretty practical for your exam. So remember, we're in Organic 2, so we expect you guys to know a little bit more about synthesis, use a little bit more of your scientific knowledge. So now we're actually going to limit your carbon source. So here it says 2-methylprop-1-ene is your only carbon source for this reaction. So clearly we're going to have to only use this reagent in forming this whole end product. So let me just show you kind of what I'm thinking about doing here. Well, the first thing is I see this alkene, and I pretty much don't know what to do unless I add a halogen. So I want to add a halogen as far away as possible. And I'll explain that in a second. So I wanted to do something like this. I hope that makes sense. All right. And this whole chapter has been about organometallics. So I kind of probably want to turn this molecule into a cuprate. So let's do the lithium reaction, organolithium reaction, to form this molecule. Okay, and then let me convert it into a cuprate. Okay, so that is going to be copper iodine, also dissolved in ether. Okay, so that is going to be this structure. Okay, so that's our cuprate. So we can use that molecule to attack some sort of halogen to basically make this molecule form. So if I took this molecule and reacted it with this molecule, wouldn't I just get that end product? Well, yeah, that's how we formed this synthesis. So again, that's what I mean by using your only carbon source. We actually generated a halogen, an alkyl halide, excuse me, and we generated this cuprate, and we used both of those reagents, let me just highlight them, and reacted them together to form that end product. So I hope that made sense on how you guys formed this reaction. It's a very good practice for your exam, because I do suspect that you will have something along the lines of a cuprate with an alkyl halide mechanism, a synthesis problem rather. So I hope this video really helped, and a chapter 16 review video will be posted shortly.